Since we began this unit on Friday, we've talked about objects maintaining their current state of motion. In other words, we've talked about objects not having a net force acting on them. We've talked about objects either staying at rest if they begin at rest, or staying in motion in a straight line at a constant speed if they're already in motion. But the reality is sometimes objects do accelerate. Sometimes there is a net force acting on something, and that net force causes an acceleration, causes something to speed up, slow down, or change direction. Tell me the two things, please, that acceleration depends upon. The rate of change of velocity. What does it depend upon? One thing we just touched on. The force. Not just any force, but the net force, the unbalanced force. It depends upon the net force. Remember, the unbalanced force. What else, though? What's going to affect the amount of acceleration? Okay, let me give you a hypothetical situation here. There's a smart car out in the parking lot, and I push on that smart car with a force of 10,000 newtons. There's a 1973 Chrysler New Yorker out in the parking lot, which, by the way, weighs a lot. I push on it with the same force, 10,000 newtons. Do they accelerate at the same rate? No, they don't. Which one accelerates quicker? The lighter one, right? The lighter one, the smart car accelerates quicker. What does acceleration depend upon? How hard I push, but also the mass of the car or the mass of the object that's accelerating. It depends upon not force, it depends upon net force, the unbalanced force. Okay, remember, Nick pushed on his desk, I pushed on the desk, the net force was 0, didn't accelerate at all. But if Nick pushes on a desk and I push less, then there is a net force, okay, and the amount of acceleration is going to depend upon how big that net force is, but also how heavy the desk is. Someone sits on that desk, it doesn't accelerate as quickly as if there's nobody in it. So what does this come down to? Well, this comes down to Newton's second law. First law was object at rest stays at rest, object in motion stays in motion. The second law also has two aspects to it. The first aspect says the acceleration of an object is directly related to the net force. In other words, if the net force is bigger, the acceleration is bigger. If the net force is smaller, the acceleration is smaller. If the net force is to the right, the acceleration is to the right. If the net force is upwards, then the acceleration is upward. Everything you do to force, to net force, the same thing happens to acceleration. That's what directly proportional means. Okay, the net force, the acceleration is directly proportional to the net force. In other words, we're going to say F, which is a vector, F net is directly proportional to, that's a symbol for related or directly proportional to. Whoops, it should have been A though, not F. A is directly proportional to the net force. F gets bigger, A gets bigger. It's not equal to it, it's just proportional to it. Now Newton's second law also says the acceleration of an object is inversely proportional to. What does the word inversely mean? What does inversely mean? Opposite, yeah. As one goes up, the other one goes down. It's inversely proportional to or inversely related to the mass of the object. In other words, A is not proportional to M, but rather A is proportional to 1 over M. When we combine these, A is related to F, A is related to 1 over M. We combine them to get this. A is equal to F net over M. This is really Newton's second law. The first law talks about when an object is not accelerating. and it's at rest and it stays at rest, it's moving at a constant speed and it stays moving at a constant speed. The second law talks about the objects that are accelerating, when there is a net force causing something to speed up or slow down or change direction. Now, essentially, we stated Newton's second law as an equation, right? A is equal to F over M. Sometimes we see it written a little bit differently. F is equal to M times A means exactly the same thing, right? Just remember that when you see it written either way, that force is not just any force, it's the net force. It's the unbalanced force. M stands for mass, A stands for acceleration. The units for force, you guys have probably seen this before, right? Who do you think would have done enough work with forces to get a unit named after them? Could be, maybe it should be. But it isn't. Who did enough work with forces to get a unit named after him? How about a Newton? The unit for force is newtons. What about mass? That's going to be kilograms, right? Standard units for mass is kilograms. And acceleration is meters per second squared. Now, it's a little bit confusing, right? Why a kilogram and a meter per second squared gives you a Newton. Just trust me on it for now. Okay, a little bit later on when we're a little bit further, I can derive that for you and show you, prove to you that they mean exactly the same thing. Just trust me for now. Notice one more thing before we do an example. Mass is a scalar. Acceleration is a vector. When you multiply a scalar by a vector, you get a vector. Scalar by a scalar is a scalar. Vector by a vector is a scalar. It's like two negatives. Negative by negative gives me a positive. Okay, but a scalar by a vector gives me a vector. Let's do an example and then we'll wrap it up for the day here. It says a lacrosse player, this is chapter 3 by the way if you don't have that downloaded already. A lacrosse player exerts an average net horizontal force of 2.8 newtons forward. Average net force, not just force, but net force. We're going to find the average acceleration. We're going to say F net is 2.8 newtons, and we're going to define forward as positive. The mass, for the first time we're doing a problem where we need the mass. We're going to find the acceleration. We're going to say F equals ma, or A is equal to F over m. Even though F is always the net force, sometimes we leave out the subscript just for a time savings. 2.8 newtons divided by the mass of 0.14 kilograms gives me, I think that's 20. Units, meters per second squared. Do you know that you could also put newtons per kilogram? It's the same thing. I would accept either one of those. Now, what did I tell you last unit about significant figures? Until after your first unit test, we weren't going to take off marks, right? Now we are. This should be 2 digits because this is 2 digits and this is 2 digits. Final answer should be 2 digits. All right. Homework, not very much tonight at all, guys. This is going to take you maybe 5 minutes to do. Page 149, 1 and 2.